Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to electrically restore a pretty high-tech radio receiver from the 1930s. So high-tech, in fact, that many companies, even today, are still using this same kind of idea. This radio also has the ability to receive high-fidelity AM. So together, we're going to electrically restore this radio receiver, align it, and then we'll see how well it performs. We're going to make it perform like it did back in the 1930s. So let's get started. Here's the radio that we're going to be electrically restoring today. As you can see, for the 1930s, this is an extremely complex radio and was worth a lot of money. Really, this thing is a communications receiver in a wooden case. They did a beautiful job on the woodwork. This is all the original woodwork. And as you can see in the grill cloth down below, that gold-looking grill cloth in the leaf, just the amount of effort put into that alone to make it look that good. All original. So this radio is an excellent example to do an electrical restoration on, and then we can see how this thing will perform. So after the restoration, this thing should perform just like it did back in the early 1930s. So everything works, all the dials and everything moves. So there's no problems with that. The little indicators for the fidelity and the volume on the top. So you'll see fidelity right here and volume. Little indicators move back and forth. There's two little sliders in there. It has a trifocal tuning electric eye. It's got all the neat stuff. So it should be a great electrical restoration. So what I'm going to do now is I'll turn this unit around and we'll take a look at the backside just before I take the cabinet out and get started. On the backside of the radio, you can see that big label that says Acoustical Labyrinth. So if you look into some modern day ideas dealing with sound, you'll find that some modern companies are using something that's very similar to this design that was used back in the 1930s. We look up just a little bit. You'll see the cardboard pipes running from the back side of the speaker down into the acoustical labyrinth. Right in the center of the speaker, right there, is an electromagnet. This is before speakers had permanent magnets. So the high voltage from the radio goes through that cloth cord, that big transformer on the corner there. The high voltage created by that transformer and rectified by that tube goes through this brown wire right here into that electromagnet, and it magnetizes it. So the current draw of the entire radio is usually placed upon that. Now, in some designs, it isn't, and I haven't looked at the schematic for this yet, so it may or may not run through that. Some of them will have a separate inductor in line with high voltage to filter out any type of hum or anything like that. So we'll take a look at the schematic here in just a little bit and see where they've actually placed the electromagnet down here in the electrical design. Lots of tubes on the chassis, very complex chassis for the 30s. Again, very expensive high-end receiver. So being expensive and high-end and in such good condition, this will be a lot of fun to electrically restore and see how this thing performed way back when. I bet you it performs very close to a lot of modern receivers. All right, I've got the back side off here, so I'll show you that. I've moved it out of the way already. Many screws later, lots of screws around the perimeter here and around the two cardboard pipes that run into the labyrinth. So I removed all that. So now this thing should just slide right out, and let's take a look at what's inside this thing. This should be exciting. That wasn't too bad. I thought this would be stuck in there, but it actually came out very easy. Okay, so I'll just slide this over here for a moment. We can see that we have a port on the bottom here, and it also looks like there's a bit of a port or a catch for the bottom side of the speaker as well here. So look at these pipes. That's pretty high tech for the 30s. Look at that. And if you look, you can see the path that goes down that way. And then there's an opening down in there. I don't know if you can see that. And it goes through kind of in a zigzag pattern through the labyrinth. So I know many of you are going to look this up And again, you'll see some modern companies are using the same sort of idea that Stromberg Carlson was using way back in the 30s. Pretty neat stuff. Still really nice and solid and in excellent condition as well. So now what I need to do is disconnect the speaker. So I'll unplug this wire from the radio chassis and take the screws out because I can't service the radio unless the speaker is attached. Again, there's current going through this and into the radio, right? So the speaker has to be there when the chassis above, which is outside the shot right now, which is serviced. So I'll get all of that taken out, get this on the bench, and we'll take a look at the chassis and the underside. That's where the real interesting stuff is. The speaker is in really nice condition. You can see the seal for that box in the back side of the speaker cabinet there. The labyrinth, I guess you could call it. Big electromagnet. Some of the paint is coming off, not a big deal. You can see they've bent this nice piece of thick metal here, and they've used an arc welder to tack it into place. So very nicely done. Now the paper that they're using, it almost looks like it's plasticized, which is very interesting. It doesn't feel like paper. It feels like plastic, but yet it has the grain of paper. It's very interesting. It has a felt surround, really soft felt, and the travel of the speaker is very fluid. Lots of travel there. You can probably see it on an angle better. Lots of travel. There is no, grab it from each side here, no binding at all. It's absolutely flawless. So when you come across an older speaker like this, you can actually adjust this in the center. If it's binding, you can loosen this off and readjust it by sticking shims down in here and then retightening it back up. That really makes a big difference, especially if the coil is touching the magnet, the electromagnet or anything. You'll notice that all the lows will go away and it'll kind of sound like, you know, you're talking with a pinched nose. Whereas in this case, everything is very, very fluid. It's working very, very well. I can see that right here. So the speaker itself is just in absolutely fantastic condition. The surround is very soft, so this should develop low frequencies very nicely. So a really nice example of an old electromagnetic speaker right here. I don't know if it gets any better than this, to tell you the truth. That speaker is just absolutely fantastic. So I'll go grab the radio chassis because all of this stuff is almost too big to fit on this bench right here. So I'll move this out of the way and I'll go grab the radio chassis. We'll take a look inside and see what we're up against with that. Here's a look at the top side of the chassis, and as you can see, it has a lot of tubes in it. So these are all tubes here and here, all over here, here, and then there's a magic eye tube at the top. It's got this monster power transformer, which makes this chassis very heavy. And it's also difficult to get out of the cabinet because you have to bring the chassis back and then tip it forward. So you have to tip it on an angle because the dial glass in the front is so high that it actually doesn't come out of the cabinet square. So difficult to get out, and again, very heavy. Now, this radio receiver has a lot of power delivering capability, so it can, I guess you could say, drive a speaker quite nicely. So these are the audio output tubes right here. You can see how big these metal tubes are. And they're 6L6s. So, this thing is definitely going to produce some audio. Let's put it that way. They used a really big rectifier. It's a 5Z3 here because, this thing obviously has some current demand with all of these tubes. So IF transformers over here, and of course we have the antenna oscillator and RF section over here. All the tuning will be, this will be quite a job to tune this thing. There are a lot of spots to tune here. And of course with the IF being variable, it definitely makes for an interesting tuning job. So I'll just move this forward here. Man, this chassis is so heavy. So I'll just put this here and take a look at the dial face. So it's in absolutely fantastic condition again. So you can see they have dial strings here. It'd be nice if I could get all of this into the shot at the same time here. Okay, I think that's about good. So you can see all these dial strings here. And you can see that when I move this, You look at the volume up here. Now there's a light behind that, and it actually shows you your volume level here by moving this little red bar in and out. So a little disc is turning in there. And then the fidelity is the same way. So the fidelity control, you can see, moves up, and then it gets to about halfway, and then it hits a hard spot, but you can still move it quite easily. Now what's happening in here is there's a cam underneath the chassis that's moving slugs up and down inside of the IF transformers. We'll take a look at that shortly. There is a bottom on this radio receiver here, and I haven't removed this yet. There is only one screw in it, so we'll discover the fun together. We'll see what's underneath this thing. And the bottom is even in very nice condition. Very interesting choice of chassis paint. Really nice look to it. So I would move this around. This is just going to move around the dial indicator behind here, but I would need a knob on this to move this because it's, has a ratcheting function inside. So it holds it into each position of the selector switch, which moves this up and down. So it takes quite a bit of force to move this. And then of course this is just a, standard on-off switch and a potentiometer variable resistor behind it. So what I'll do is I'll flip this thing upside down. I got to do this very carefully. Have to be very careful with this dial glass and everything like that. And we'll take a look under this cardboard cover and see if anything has happened over time. It's obviously been serviced. There's a nice big hole here where probably some filter can has been removed or something like that. So it looks like it's actually painted. Yeah, I would imagine something was sitting there and has just been removed. All right, let's take a look at the underside. There's only one screw in the bottom here, so obviously people have been in here before. Not me. Somebody else has been in this thing. I have worked on these chassis before, but not this one. Look at this. Moisture resisting fiber. All right, no cost spared here. Whoa, no restorations done here. Looks like it's been patched up through time though. And look at this. Tar's even melting on that transformer. I'll grab the bottom here again. Let's take a look. Yep, there it is. Why is this here? Well, because of these. So what happens is these capacitors end up shorting out or becoming resistors, and they cause circuitry in the radio to draw heavy current, and that heats up components. The components get hot, the tar melts and starts to flow. And you can see this one here has got a little bit of tar on it as well. So it's quite a ways away from the edge of the chassis here, so components have definitely gotten hot. This one here, really hot, so hopefully that's still okay. We'll find that out when we verify the radio. So the most common thing that destroys these old radio receivers is when these are purchased, people tend to grab these things and they bring them home and they think, oh, I want to just plug it in and see if it works. And when you do that, what happens is these capacitors, they end up shorting the electrolytics, and even these old paper and foil type capacitors, they end up shorting out, and they burn components out inside of the radio, and sometimes even the large power transformer that's way down in here. So if the power transformer burns out, that's kind of a crucial component on these chassis, and you have to end up looking around to find a replacement. Look at how hot this one has gotten. The actual color bands have changed on this. And, well, what's attached to this lead? A sealed tight capacitor. Sealed tight to keep the leakage in. So, definitely bad components all over the place. So anyways, what destroys these things is these cylindrical things right here. So all of these have to go. So this has to go, this. Oh, I can go forever. So there's a lot of them in here that have to go. So what I'll do is I'll remove these. These very easily come out. You just remove these screws here on this side and on this side down here. And then I can take these out and I have a nice free, area to work in here. And I can start replacing all of these components. This is the variable IF right here. You can see these slugs. There's a slug here and a slug over here that'll move up and down with this control. See that? How these are moving up and down? So there's a tone control here. There's a variable resistor here. And then this comes down here, and then we can move this up and down. This will change the fidelity. So we'll take a look at this on a spectrum analyzer. You're probably asking, why aren't you working on this on the bigger bench, on the old-time workbench? Well, reason being is because I don't have the 3585B spectrum analyzer out there, and we want to take a look at the IF in this thing. So I have to do it on this bench. So there are some original capacitors. This one here says Stromberg Carlson on it. I can see the people that have put this together have actually spent the time to put the capacitors in the correct way. You can see outside foil mentioned here, that ties to the chassis. Outside foil ties to the chassis. And you can see here, we have the outside foil end tied to the chassis. So they have spent the time to put this thing together correctly. So as I've mentioned before, whenever you're working on a radio receiver like this, it's worth the time to locate the outside foil on the newer style capacitors because they aren't marked. And I've designed a little device to do that, and I've released that, the plans and schematics and everything for that on Patreon. So you can take your new capacitors, locate the outside foil, and put in your new replacement capacitors the correct way. So they spent quite a bit of time to make sure that this is all done correctly when they put these things out of the factory. So you want to make sure that when you're doing your restoration job that you take as much time to do the job correct as well. Now what I'll do is I'm going to start replacing all of these caps here, and when I have that done, I'll come back and we'll talk some more about this. So what I'll do in the next shot is I'll tell you the amount of time it took for me to replace all of these capacitors. I.e., okay, it's been 2 days since the last shot, or it's been a day, because you really can't tell because in seconds it blends into the next shot, right? And I'll give you an idea of how long it takes me to do this. Now, I don't, cut corners and do the J-hooking method. A lot of people like to do that. They'll just cut the capacitor and leave a little bit of lead, and then put the new capacitor in it, and then J-hook the leads together. I don't do that. I'll actually remove the lead right from the terminal tie strip, and I'll put the capacitors in like they were at the factory. So I'll install them like that. So that takes a little bit more time to do that, but I prefer that method. So I'll get that all underway, and then we'll go through this and start testing some resistors. I'll even keep some of these capacitors out and we can test them, and I'll give you an idea of how these things fail. I'm interested in testing the Stromberg Carlson capacitor. That's an original device right there, and yeah, it's put in the correct way. The band end is here, and that's right to the braid over here. So everything is, they spent the time to do this correctly, and even the people that were in here later on that did the work, like this looks like a replacement part right here, they even put that in the correct way too. So the technician that was in here at some point in this thing's repair history did understand that it's very important to do that. And I'll talk more about why it's important to actually put these things in the correct way, even though the newer capacitors don't have it marked. Just before I start recapping this thing, which at this point looks like an endless job, I was going to show you a modification that somebody has done throughout time. I don't know when this has been done. At any rate, somebody has cut one of the capacitors here and then tied some shielded lines in and, reattached it to the volume control so that you could pump some form of external music source or something in here at any rate. So I want to return this thing back to factory spec as close as I can so we can get a really good idea of how this thing sounded back in the 1930s. So all of these modifications are all going to be taken out, because when modifications are done like this, sometimes they introduce hum, even though they have shielded cabling, just because of their ground connections and things like that. And I don't want to introduce any other issues from other people's, in this case, scary looking modifications. Like it's black tape up here, tape to a resistor, and all this kind of stuff. Green wire running off to here, just, some pretty scary workmanship. So this has been done over time, and this is very common when you work on radio chassis like this. A lot of the times you'll find yourself referring to the schematic to go, okay, so what's been done doesn't make sense. Let's try and figure this out, kind of thing. So I will show you the schematic here in a little bit, and we'll go over it, and I'll briefly explain the way that this radio operates. I have already gone over the entire schematic for this radio receiver up on Patreon. I spent a lot of time explaining all the different parts and sections in it, as there is a schematic series going on up there right now. So at any rate, I will go over it briefly here as well, and show you what's been done and do a brief explanation of this circuit for all of you as well. Through the magic of the camera, what you see here is about 16 hours worth of work, give or take a half an hour or something like that. So it's been roughly 16 hours since the last video clip, and these are all the components that have been replaced in the bottom side of that chassis. And in a moment, we'll take a look at the bottom side of the chassis, and I'll show you how I've mounted all the new components. Now, you may look at this and say, well, it doesn't look like a whole bunch of parts. Why did it take 16 hours? I was actually working pretty quick. Reason being is you have to move other pieces out of the way, and as you're replacing components, you're also testing other components that are attached to the same tie point, so you don't solder a new component in and have to go back later, test a component, and then remove, say, a faulty resistor. So for example, if this was tied to a tube socket and this was tied to a tube socket here, well, I'm not just going to desolder the capacitor, right, and then replace the capacitor and then come back later on and then test the resistor, find that it's faulty, and then have to desolder both of these again, remove this, put a new one in, and then resolder it. So there is quite a bit of time in just basically going through everything and testing all the components to make sure that they are close to value. Now, when you're replacing these components, you can optimize the design, and it's just due to the newer components. You can get grounds closer to where they need to be. Instead of running it to a remote part of the chassis, you can actually, ground it directly. Say if it's a bypass capacitor, you can go right from the screen to the cathode or very close to it on the chassis area. You can really optimize things, and that's just due to component size now. So for example, this capacitor here is the cathode capacitor on the 6L6 tubes. And this is located way across the chassis because of its size, right? You can see it's a pretty large capacitor. So this capacitor here is replaced with this capacitor right here, one of these caps. So you can see the difference in size. Now these have very good temperature ratings as well, so I can mount this very close to the socket of the 6L6 and ground it right beside it, which again optimizes the design. I don't need to carry a wire all the way from the cathodes of the 6L6 across the entire chassis and then mount this way far away. So things like that, and that really helps in RF service too. Whenever you're installing bypass capacitors in RF service, you want to keep them as close to the device as possible. You don't want long leads because long leads act as inductors, and they also pick up noise in sensitive applications. So I'll talk about that when I get the chassis here, and I'll give you some of my ideas and thoughts as I've gone through this and optimized things as I've been replacing components. Here's another capacitor, something like this here, brand new. We'll replace this right here. Okay, so, and they even get smaller than this. This is a fair size capacitor. You can get these capacitors, I guess you could say, size optimized as well, and I'm not really too worried about that. These are very long life, high temperature capacitors that I use. So I'm doubting that those will need to get replaced for an extremely long time. Very high quality electrolytics. I have entire lists. I've spent time grading, countless hours grading and testing components and verifying them in order to use in these older radio receivers so that, it keeps the radio receiver working incredibly long. I have those lists up on Patreon. I have a couple of those verified components lists up there with part numbers and everything. So if you're restoring radios, that may be beneficial to you because I'm, I guess you could say, a little bit picky about what I do. So what I'll do is I'll test some of these components here, and I'll show you where the real problems were. And just by removing these components and testing them, I can tell where the radio would have failed. So I don't even need to turn the radio on to do this. I can just go, okay, this is bad, so that means that this is going to happen. Or this is faulty, so this is the result of that being faulty. So what I'll do is I'll start explaining some of this. I'll get a schematic in the shot, and we'll test the famous death capacitor as well. So this is the capacitor that's across the AC line and tied to the chassis. Now these capacitors are, it's given a pretty strong term, and they call them the death caps. But really what happens with these things is they end up short or becoming electrically leaky, and they bring the AC line onto the radio chassis. So this is that capacitor in that radio. We'll test this as well, and we'll see exactly what's gone wrong in here, and I'll explain all about all of these components here. So I'll go grab a schematic and some tools here, and I'll talk about that, and then I'll grab the radio chassis, and I'll tell you where I've replaced things and why I've done it like that. Okay, so here's the schematic, and for any of you that are owning one of these Stromberg Carlson radios, they're very cryptic about these resistors that are basically sealed in a block. They don't have any resistance ratings listed anywhere, so what ends up happening is capacitors fail in these radio receivers, and that resistor block goes open, and then you're left scratching your head going, what really was the resistance value there? So I've taken the time to mark that off, so any of you that have a failing one of these radios, let's say, that has that burnt out resistor block, and it's very common when capacitors fail and people operate the radios, right? So when this fails, these are the resistance values. So there's 3 resistors inside that resistor block, and I'll show you that here when we look at the bottom of the chassis. I actually just write right on the resistor, right on the little strip that holds it down, I write the resistance values, so in the future, if something ever does go wrong, it can very easily be replaced by somebody else or myself, right? So these are the values. So we have a 630 ohm resistor right at the top here. There's a 12K ohm resistor right here. And then this resistor is completely separate. This is the cathode resistor for the 6L6s right here. All right, so it's 2 resistors that are put together and then one separated one at the bottom. And those are the values. Again, I'll cover that when we look at the bottom side of the chassis. Again, I'll show you the resistor. I actually put a piece of thermal transfer silicone underneath it so that it will transfer the heat to the chassis and use the chassis as more of a sink. And it also keeps it tight in the bracket, because a lot of the times they come loose because just the plastic changes size over the years, and then they get a little bit loose, and then they don't properly transfer heat to the chassis anymore. Okay, so I'll show you that as well. Lots of little things that have been done in here. So this capacitor here, the death capacitor, is these 2 right here. So you can see it has a common ground to the chassis. I'll zoom in on this. I don't know, I've got my exposure fixed right now. I think that's going to be okay. So the brightness is staying all right. Okay, so that's the center connection, which is the shell of this capacitor, and then this is each capacitor. Each one of these leads is a lead off to the line side there. Now, as you can see, this is put together properly. Stromberg Carlson used their brain when they were putting this thing together. You can see the very first thing in line is the fuse. And then after that is the switch, and then after the switch are the capacitors. So if this ever fails, it's not right across the line at the line cord, it's beyond the fuse, so the fuse will go away if this was to say dead short across these 2 wires. Okay, a lot of new designs, they don't do that. They have the fuse in other places and things like that. You can even see there's a different version of this Stromberg Carlson that has a phono adapter, and it's kind of a skyscraper-y looking radio. It's a pretty sought after, very rare unit as well. And you can see that they've got the phonograph after the fuse and the switch as well. So everything is protected by that first fuse in line. That's very important in a good design. So this capacitor here is replaced with a modern X1Y2 rated capacitor. So there's 2 of them, all right, one for each one. They're X1Y2, so they have very good safety ratings. They're actually a certified safety capacitor. So when they fail in the correct mode. They don't, cause issues. Okay, so they're known as X1Y2 rated safety capacitors. If you're more interested in that, you can look those up. In fact, I have a bunch of those capacitors, again, listed on that verified. I believe they're in the verified components list. That may have been done after that. If not, it'll get added at any rate. So these resistors here are the ones that I just talked about, that long one on the back side of the chassis. These capacitors here have all been replaced by these modern caps right here. And then, of course, this cathode capacitor right here is the one that was replaced by these little guys right here. All right, my focus is right here. There we go. All right, 105 degree rated caps, long life, very important. Now, get rid of this thing. So these capacitors here, these 2 want to hang out together. So these ones here are down here. So there's one of them that's down here. All right, that's right across this particular unit right here and right to ground. So it's funny, they show a dot in the center, but they don't show it tied off to ground, but it is actually tied off to ground. So one of these caps right here, and there's a few things in the parts list here that aren't even listed, which is kind of interesting. The parts have a number on here, but they're not listed, i.e., part number 175 isn't on the list. Things like that. Anyways, these capacitors here, this is basically a 10 kilohertz filter right here. So to keep the highs, I guess at bay, you could say, because the IF in this thing is very wide. And with these 2 variable IF transformers, you're going to get some pretty high fidelity sounding AM out of this thing. So there's a bunch of these things in here. You can see I've replaced these here. Now, it's kind of a little bit odd because they use two different types of capacitors. You can see this one says mica mold on it. Okay. So the mica molds, these 100 picofarad capacitors, are leaky. Now, a normal capacitor tester won't detect this. So these look fine on a normal cap tester. Even on a normal leakage tester, they look absolutely fine. But these are actually leaky. They are degrading. Now, there are other capacitors in the actual radio chassis that say made in Canada, and I'll show you those ones there. Those ones are all okay. It's just these mica mold ones here that are, you know, a problem here, especially the ones that seem to have the two leads sticking out. Here's another one here that was doing some work in the RF band switching section. Okay, so this one here, I had to remove this resistor from this one side here to test this, right, because this would act as leakage, right? And yeah, all of these mica molds here, they seem to be, you know, creating a bit of an issue. So this one capacitor here was in the RF section here somewhere. Where was it again? It was this one here. It was this one here. And then there's a resistor across one of these right here. You can see this here. This resistor goes right across this one right here. So this was replaced with newer mica capacitors, right? Let's see, what else can I tell you here about this? There's so many parts and pieces all over this. These 47 k ohm resistors were moved up in value. The cathode bypass capacitor, this one here, is virtually open, so it would have really lost the bottom end response, and that's this capacitor right here, would have really lost the bottom end response, and the loudness effect would have, you know, really gone way down on this. This part here is a part that's gotten very hot, and of course that's because of failed components. This radio was being used, let's back this out here. This radio here was being used like this up until not long ago. So there has been heating in some components that would, yeah, it is definitely apparent, as I've mentioned before. And some of these capacitors are so incredibly bad. Some of the original capacitors in this unit are so incredibly bad. This thing was on the verge of a really catastrophic failure. So, and I'll give you an example of that here quite shortly. So lots of parts and pieces replaced throughout this entire unit. Whenever you're working on one of these radios, there's a little part that hides by the tuning eye, and it's usually right in the tuning eye cap itself. That one always should be checked. It's usually a 1 mega ohm resistor. So there are discrepancies in parts, in the parts lists of a lot of these radios. I've noticed lots of discrepancies in this as well. So I've gone with appropriate values that make sense to other sections. Now, it could be the discrepancy that I'm seeing has been a component replaced by a technician down the line. For example, when I was looking at this didn't look right. All right, so this 2.5 k ohm resistor is actually supposed to be 560 ohms. All right, so there would have been quite a bit of voltage drop across this one device, and it would have caused the receiver to be not as sensitive as it could be. Okay, so I replaced this with the appropriate value, and of course, you know, we're yet to test this thing out. We'll see how it all works when we turn it on for the first time. This value here is one of those 560 ohm resistors. It's been very, very hot, and it's because one of these capacitors was very, very leaky. I believe this one here was attached to it. So this is one of those really horrible sealed tight capacitors. As you can see, it's had better days. So, and there's another one over here too. Different color, red solar sealed tight capacitor, high temperature molded capacitor that spits chunks of its molding off when it gets hot, I guess. You can see that there. At any rate, yeah, all really, really bad. So all of these capacitors here, no matter how you test them, are going to be, you know, bad in some way, shape, or form. You'll find some that are better than others. And these are kind of odd because usually these capacitors are very good. Mica Mold makes very good capacitors. This may have just been a series. Maybe it's because they've molded two of them in one unit. That might actually be the issue with this. So I don't know why these mica molds are like this, but they are. Nice looking little capacitors. Now I always save all of these things. I'll put them in a bag and they end up in a box, and I can use these as reference in the future. And then when people want to know, oh, hey, you know, I have one of these capacitors inside my radio receiver. Do you think it would be bad, i.e. one of these? I can go, yes, when I test these things. Now you'll test it on your normal tester and it'll look fine. But if you do an extensive test with the capacitor tester that I've created, you can really see the problem in this. I created that capacitor tester because I was working on transmitting gear, and some very high voltage mica capacitors were not showing any problems on any test equipment, even modern stuff. So I had to design my own piece of test equipment to find the problems, and it sure enough did. It found the problem. I replaced the mica cap, and the transmitter was back in service and nice and happy again. So anyways, I'll show you that here in just a little bit as well. So anyways, this is the, just a quick run over of the components here. I'll get some test equipment and I'll show you exactly why these things are failing and what's going on inside. Here's a very good capacitor leakage tester that's readily available on the used market today. When they're rebuilt, they're very sensitive and they work very well. However, when testing some capacitors, they just aren't sensitive enough, even in the mica position, which is the most sensitive leakage testing position that this capacitor tester has. Now, these capacitor testers, they put quite a bit of applied voltage across the device to test it. As you can see, this one here will put up to 600 volts across the device. And keep in mind the current is low, but that is still 600 volts. And caution needs to be used whenever you are using one of these devices. So if you ever do get one of these things, definitely follow the safety instructions that are, issued with the device. And it's always a good idea to keep it in the discharge position. The switches aren't spring-loaded, at least in this model it isn't, so it won't automatically pop back to discharge. You always want to make sure before you touch the leads or anything that it's in discharge and the voltage is turned right back down to its minimum. That's just a few extra safety precautions when using a device like this. So keep in mind, if you are going to purchase something like this and use it, you are definitely doing so at your own risk. Be careful. This device that I've designed is a low voltage tester, so much safer to use, and it's much more sensitive as well. It's designed to find those obscure issues. And I'll give you an example of that right now. So here's one of those capacitors that I've taken out that on this unit will test absolutely fine, but this one here will show the failure point. So I've mentioned this before, okay, in many of my other videos about these types of capacitors in the oscillator and RF section. If you don't have to replace these mica mold or mica capacitors in those sections, definitely don't do it. So you want to test them to make sure that they're not faulty, but if you don't have to replace them, don't just replace them for the sake of putting in a modern part. Reason being, again, as I've mentioned in earlier videos, is at the factory, many of these are hand-picked. And what they've done is they've optimized on the values to make the dial on the radio track correctly, if these are in the oscillator section. And even in the RF section, you need to be very, very careful with these caps. You don't want to be replacing these things unless they're absolutely necessary. So I hear so many people saying, oh, I just took out all the capacitors and I just replaced all the capacitors and I started from there. But now, 600 AM is somewhere around 650 and I just can't get it to line up. Again, a lot of these things, they were hand-picked to make sure that the dials track correctly. So something that may say 100 picofarad, that's what this means right here, 100 picofarad, may not necessarily be 100 picofarad if it's hand-picked. It might be 112. All right? So, and all of them that are used in those series of radios, they may have bought just tons of 100s and they just hand-picked all the 112s, and that made their radios work all that much better. So keep that in mind when you're restoring these old radios. These should always be tested and not just blindly replaced. Wax capacitors and electrolytics like this, you don't even think twice about, they can come out, right? Okay, so I'll give you an example of this here. So what I'll do is I'll attach the test leads of this to this capacitor here. All right. Now I don't want to hold the boots because this thing here has told me that these boots are mildly conductive, and I don't want to be touching those. So I'll hold the insulated leads here. So I'll click this on to leakage. If this is bad, that I should close. Okay. That's right up to 600 volts. So it shows it as being okay. Okay. So I'll turn that back down again and hit discharge. To show you that the capacitor tester is working, I'll just clip this here and I'll click this onto leakage. And as you can see, it's just, 3 volts, whatever. It doesn't matter where you go. It's faulty, right? Because it's dead shorted this way. All right. So you can see that. I'll test the other half as well. Okay, so I'll put that over there. All right, hold these apart like so. Let it fall like that. Leakage right up to the top, 600 across it. Right down to the bottom. Nothing's happening. So it shows this as being an okay component. I'll click discharge. All right, always in discharge. So now I'll move this over to here. All right, so now what I'll do is I'll test this in the forecasting position here. So there's two scales that are indicated by these LEDs here. This is a newer release of the board. I've had many patrons that have asked, hey, you know, can you give this a larger, more broad scale and something that can be calibrated to a resistance reading, and this thing can. So at any rate, this is one of the newer designs. So what I'll do is I'll put this here. All the designs work. Any one that you make works. This is just, I guess you could say, something that is more optimized if you want to actually, you know, get an idea of the actual resistance of the device or where it's leaking. So I'll put this across here. Again, I won't hold the boots because the boots are mildly conductive and this will pick it up. So I'll hold it back here. Okay, so this is in the forecast position. So if it's red, it's really bad. If the scale is yellow, it's on the second scale down towards the green light here. So this is discharge. Okay, so it's green. And then I'll click it onto test now. There you have it. It's showing the issue. You see the light's red, and we're only one LED in from the end, so that's just over 1 gigohm. Okay, so this can count all the way down here yet before this goes green. So I'll hit discharge. Okay, and here we go again. This is a faulty device. So I'll test the other one. I'll shut it off, move this over to here. I'll test the other capacitor on here. And just make sure that nothing is touching. Okay, so here we go. And that one's just a little worse than the other one. Okay. Oh, no, it's coming down a little bit. It's still very bad. So they're very, very close together at any rate. So now to give you an idea of how a good capacitor will test, so this is 100 picofarad. Okay, so if you were to test this on a normal capacitor tester, you're going to grab just a normal cap tester here. Let's move this up here. I'll put this on the 200 picofarad scale. What you're seeing is just its own capacitance here between these two things. I'll just plug two of these in here. So I'll bend this lead out of the way, and I'll just plug these two into the fixture here and get my hands away from it. If it'll fit. These are some pretty thick leads. There it is. Okay. So there you go. You can see it's in there. It tested 108. So you'd think that it's okay. The capacitance is okay. But it is turning into a resistor. So what I'll do is I'll pull this out of here and I will give you an example of this capacitor. So this is another mica capacitor. This one here is 100 picofarad. Same kind of deal, 104, all right. So what I'll do is I'll put this one into these leads now. Now keep in mind that this here is just another mica, just like the other one. This is just a different package. Okay, so there you go, in the leads. Now watch what happens. Look at that, no problems. That's beyond 40 billion ohms. Shut that off. That was through the discharge, and one more test. No problems. Okay, so that's how most capacitors are. All these micas should test in the forecast position. See if I have another one on the bench here. I do. I've got one off the side. What is this one? 3900 picofarad. Okay, so this one here should be 3900. Let's see what it reads on here. Make sure I am not leading any of you astray. I'll put this in here. It should be about, go up to 20 nano. Yeah, so there you go, 3.87, so 3900. 3.87 nanofarad or 3900 picofarad, very close to, okay? All right. So let's test this one. Now this one here is quite a bit larger in value. So let's test this one here on this. Okay, so no problems. Again, discharge. And here we go. No problems. So you can see if I just put my fingers across it, you know, I make the machine look like, or think that I'm a dead short here. See how bad this one is. This one is rated at 0.1 microfarad. So put this in here and click leakage. Wow. So there you go. This one's leaking at 6 volts. And this one is rated at what? $200. This is rated to go to 200 volts. All right, so this one is really effectively turning into a resistor. So let's see what this does here. Back down to 3. Let's see what it does on this. Still on the test position. Just hold that up there. Yikes. So the second light, between the first and second light, we're looking at, you know, 10 megohms of resistance. This one is really bad. Yeah, that's going to be about 10 megohms of resistance. That's only one light into the red, into the bad scale. So this is really bad. So this is virtually, you know, a dead short up to a megohm. This is around, you know, 10 megohms are in that area here. So I'll just shut that off. Let's, for the fun of it, let's just take a look at this. Now keep in mind that those things are across the supply lines in here. Right, and these are the ones that just destroy the radio. So I'll turn this on. Get my leads here. Turn this on to ohms. Give it some brightness here. Hopefully you can see that. I'll move the focus onto the screen just in case it's hazy. All right, so here's our cap. Let's read its resistance just for the fun of it. So it should be in the area of 10 or something like that. Look at that. So it'll keep counting for a while. So now you can see, like, we're at 3 megohms right now, and it'll probably settle off. If I let this sit for a little bit, it'll, you know, settle off somewhere. This other cap, maybe this tester here may actually give me a quicker reading. I know that that really doesn't apply a whole lot of current. So here, let's try this one. Maybe I can get a quicker reading on this. So I go here, and we'll go, say, to the 20 megohm range. I'll put this here, and let's see if we can get any kind of a quicker reading off of this. So there you go. We're at 6 megohms. Almost 7 megohms. All right, here is a good 0.1. So you can test this here, see what happens. You'll see it's just an open connection, right? You'll go, right, see, it's open. All right. And if we test this with the other meter, which goes way up into the megs, we test that with this one here. Now this is only going to apply a very light amount of current. Let's see what this does here. This here and here. Beyond 500 megohms right there, right? The reason it's climbing up slow is because it's charging the cap, right? So it's beyond 500 megohms, which is absolutely fine. You know, and of course these things test great on these capacitors here. These are all on that verified parts list. You'll notice that radio has a ton of those inside of it. So at any rate, there you have an example of why you may possibly want to build something like this. So if you do want to build this, all the plans are up on Patreon, and you'll find out that this thing is very beneficial to have on the bench. I use this continually. In fact, just for the fun of it, as I'm removing components, I actually test it with this to see how bad they are. And as you can see, that one there, you know, it may settle off, you know, around, you know, well, this is what, just about 7 megohms, something like that. It'll settle off around that area. The first light's about 1 megohm to a short. The second one will go to about 10 and a bit, and then the third one is going up. And this here is just about 1 gigohm, 1 gigohm, and then when the scale flips again to the yellow, it's a gigohm, and that's all the way to 40 billion ohms this tests. So if there's any leakage through moisture ingression in any of your capacitors or anything like that, this detects it. That's the reason I had to build this, is to fix that transmitter. And that transmitter, as I say, no problems. In fact, it's still in service. So no issues whatsoever with that thing. Now, keep in mind, all the previous versions that you've seen to this test this pretty close to the same range as this one. This one has one extra added range, so you can see when capacitors are charging. That's why it's a dual color. They're all on Patreon. All of these things I've created are up there. So if you want to build something like this for yourself, you can do that. And of course, the foil side tester is there as well. This is the tests for the outside foil. I'll give you an example here. I do this with every single cap and mark them, because these ones don't have the outside foil listed. So I'll turn this on and hold my hands up here. I'll insert some noise into this cap. So the LED with the least amount of LEDs lit indicates the foil side. So this is the foil side. See? Noise and no noise. Okay, so the least amount of LEDs with the LED here that's lit indicates the foil side. If I touch this, I ground myself out. That's the reason you can see I'm doing this here. So I'm acting as the noise antenna for these things. This is up there as well. So this is an adjustable sensitivity setting for all sorts of different capacitors, and it also has an intensify position here for those really, really sensitive ones that you're having a hard time locating the outside foil on. You can see how just clear that is, right? So outside foil, this side. So then what I would do is I would take this capacitor here and then take my little fancy pen here, if I can get the cap off, and then put a little dot here. Just like so. And that little dot now indicates the outside foil end, and this is marked for use. So to give you an example, even though these capacitors are leaky, they will have an outside foil. So you can see that this one here clearly marks outside foil on one side, outside foil. All right, so put this here and this here. And so this side here should be the least amount of lights again. Hold this, get a little bit more hum into it. Not much. There we go. So that's the least amount of lights on that side. You can see the outside foil isn't as pronounced on this older capacitor. It might also be that I have the sensitivity way up as well. There you go. So least amount of lights, the corresponding LED is the outside foil end. And again, it's this side right here. And as you can see, it says outside foil. So if I flip this around, you'll see the effect on the other side. Okay, so I'll just remove this. And I'll turn this around. So this should be now the least amount of LEDs, indicating the outside foil end is on this side, right? See that? So it's flipped around now. Again, very useful for when you're working on radio gear to put these things in the correct way, especially for bypass service and things like that as well. Another project that's up there, ready for you to build with all the plans and schematics and everything. So that's just 2 of them. I have a lot of these little devices up there that I've designed. So if you feel that these may be beneficial to you, definitely head on to Patreon and check those out. For those of you that have never seen resistors like this, they read just the same as normal resistors, except their coding is a little bit different. So if you can remember bed or bell, you can very easily decode these resistors in the future. Bed is very easy to remember. Body and dot, or bell as in body and line. So the body is the majority of the color. So the body is yellow on this, which is 4. The end is purple, which is 7. And then the line is orange, which is the number 3. So you can directly convert that last one into zeros. So 4, 7, and then 3 zeros. So 47 k ohms is what this is, or 47,000 ohms. Now, a lot of these are body and dot, so there's just a little dot on the body. They don't have an entire line drawn around it. Either or, pretty much the same type of deal. All right, so let's test this one here. This is the same type right here, so we'll just go across this one here. And as you can see, that's a long ways away from 47 k ohms. It's 55 k. Right? That was replaced. Here's another one. Same value. Look at that, 61k ohms. So these are way off, right? This one here was supposed to be 560 ohms was supposed to be. Somebody had replaced this, and it turns out that this one here is 220 ohms. So all the colors are burnt on this, and this is most likely from that bad sealed tight capacitor, nothing else. There's nothing that should really heat this resistor that hot. So this one right here is the reason that this one got so hot. So this was dragging, there's B plus on one side of this, and then of course this is dragging the other side down, making this thing change color. And even the color bands have changed, it's hard to read now. So that was replaced, and then this resistor here was in a spot where there should have been another 560 ohm resistor. This one here may be okay, so that should be 2.5k. That's 2.8, not too bad. At any rate, so this was replaced with a 560 ohm resistor again. Now, that's just a sum of them there. There's more of them that are scattered around the bench here and everything like that. So those are way off. Now, keep in mind that no fourth band or anything means that these are all 20% tolerance. So, depending on its application, if this was 55K, it would be okay in some applications. But whenever there's current passing through this, and it's, say, supplying a screen section or something like that in a radio where there is a bit of current demand on it, if it's supposed to be 47K ohms, it should be replaced with something close. If you lower the screen voltage on certain stages, you'll also lower the sensitivity of the receiver. And of course, when you have resistors like this in the wrong area that are, a lot higher in value, let's put it that way, that definitely needs to be changed as well, because there's going to be quite a bit of voltage drop across that resistor. And of course, again, the receiver sensitivity is going to be affected, again, especially if it's powering up the screens in the radio receiver, or say it's in line with a transformer that runs to a plate of one of the vacuum tubes, something like that. There'll be a lot more drop across this than there would be a 560 ohm resistor. Here's the bottom side of the chassis with all of the replaced components, and as you can see, they are everywhere. All of these yellow devices are all brand new capacitors. These are all brand new caps over here, all of these electrolytics. You can see the resistors that have been changed. This is that one that got really hot. And there's the 47k ohm resistor over here that was bad, another 560 ohm here. All the caps, these are lots of electrolytic caps have been reinstalled. They're all over the place. These are the new caps that are across that 10K filter in the audio section. There's more of these under here. I had to remove this little tar-filled transformer, tar-coated transformer. Just the amount of work that's gone into the bottom side of this thing is very incredible. The known death capacitor that used to be here is now replaced by these two components right here. In fact, I forgot to actually show you how bad that cap is. It's over here. Maybe we'll revisit that here in just a little bit. This is the death cap. So it is very leaky. So these are the X1, Y2 rated caps across the line there. I left the original line cord in because it's flawless. The original cloth cord is soft and it's absolutely flawless. Now this line cord is not to be confused with a curtain burner. This is not a curtain burner line cord. This is it has solid wire in it. You'll hear the term curtain burner. What that is a resistive line cord. So the actual line cord of the radio receiver itself is a resistor, and that was used in some of the early series sets to create a drop across the line cord so that the tube filaments in the radio gets the correct supply. So again, those resistive line cords are known as curtain burners. Now they look a lot like this, but this is a standard line cord. It's just standard copper wire in this. So no problems there. And again, it's flawless. Like the line cord, there's not even a nick in it. It looks, completely fine, and it's soft and pliable and flexible. So it's kind of nice to leave that on there because again, it, just maintains the original view of the radio on the outside. So that's really good. What else can I tell you about this? These are these made in Canada caps here that are just absolutely fine. There's no problems with those. And zoom on into that. You can kind of see that. So, made in Canada right there. Those ones seem to be okay. Now, mind you, a lot of the waxies were made in Canada as well. I think the Stromberg Carlson ones were made in Canada. And of course, anything, see, made in Canada, these things are just horribly leaky. So these are really, really bad. So the micas are okay. The paper and foil caps are the exact opposite. So those are very, very bad. So lots of work done under here. The filter caps that were in here have been replaced by these modern Rubicon capacitors. They're very, very good capacitors, put it that way. Oh, this is the resistor on the back that often fails. That resistor I was telling you about that they don't give you any ratings for in the parts list or anything. So this is it here, and as you can see, I've actually drawn in, it's on a bit of an angle here because of the way the radio is sitting, but you can see I've actually just written down or drawn in the resistors where they go and put their values there, right on that little strip. You can see on the back side here, I've taken a piece of that, basically it's thermally conductive silicone. It's designed for putting semiconductors against heat sinks and transferring the heat to the heat sink. So it's resistive, and I've also put that underneath here. What happens is, over time, this plastic body of this resistor, or the compound that they're using at any rate, shrinks up a little bit, and the bracket gets loose. So by putting this underneath here, it acts as almost like a cushion, and in the tight spots, it's very tight, and it also, it can expand into the areas that aren't so incredibly tight. So it makes nice thermal conductivity all the way across the entire resistor body to the back, and it keeps everything nice and cool. So that's just something that I normally do. And there's no heat sink compound or anything on it. It's just, that piece of heat transfer silicon underneath here, and it's tight on there. Like, it just, it's really tight. So that'll keep that in very good condition. If this isn't bad and you replace all the caps in here, chances are this will not go bad. It's just the capacitors that destroy these things. Sometimes I've seen holes burnt right in these things. And what happens a lot of the time too, they get so hot in one area that it chars the area, and that area becomes conductive, and then the actual resistor from the B plus section, it makes somewhat of its own resistor because the material has gone conductive to the chassis, and it just makes everything all that much worse. So they burn holes in them and everything like that. So this is a nice barrier between that and the chassis as well on that one side. So it's just a win-win situation doing that with these resistors here. That is pretty much it. That's all that's done here. And, on the bottom side, at any rate, I haven't cleaned the band switches yet. I need to still spray the switches with contact cleaner, and I will do that. And the next step after that is to basically turn the thing on, see if it works, see what happens. Oh, one thing I didn't do either is I didn't check the little resistor where the eye tube is. Why don't we do that right now? I don't know if you can see that. Get that right into the shot there. Let's see. I'll grab a screwdriver here and open this up, and let's see what it is. Too big. Let's see. Where is the correct size? That is a little small, but it'll work. Okay, so these just usually pop open. Just pry them up. So a little bit of area around the side there. You got to be careful. You don't want to break anything. See, there's a little index here as well. So when you put it back together, you want to put it back together so that index lines up with that. There it is. See if I can just pop that out with my fingers. Nope, that is pretty tight. Yeah, it's pretty tight, all right. Let's see if I can get behind the second layer here. That should give me a little bit of leverage. There it is. Okay, there is that hiding resistor. That's 1 megohms. Again, body end dot, brown, 1, end is black is 0, and then green is 5 zeros. That's 1 million ohms. Okay, so let's see if this is going to be okay. Grab my meter from across the lab because I wasn't expecting on doing this. Let's see what happens. Does it need to get replaced or not? Turn this on, just lay that in there. Get a bit of the glare off that. Okay, let's see what happens. That pin to this pin. 1.55. Not good. That needs to get changed. So 1,500,000 ohms. So that's already halfway to another meg. So that needs to go. So there you go. So if you ever have an iTube that's not as sensitive as it should be, you definitely want to change this resistor. And as you can see, this resistor needs to get changed. Again, it's, halfway to another meg ohm again. So 1.5 meg ohms is way too high. This should be 1 meg, in some cases even just a little bit lower. So I'll change that out, and I'll go grab the speaker. I'll flip the chassis over, and we'll see if the thing receives anything. All right, place your bets. What do you think's going to happen? So do you think this thing's going to work, or do you think we're going to have some magic smoke? Hopefully not. So before I did anything here, I put 2 knobs on these 2 controls here that are a little bit hard to turn. This one here is the IF bandwidth, and when that little arm comes over to move those 2 slugs up and down inside there, it does get a little bit rough to turn. And of course, this one here is the band switch, and it has that little ratcheting effect. So I put 2 just junk knobs on here, and the other 2 are just plain. I can just twist these around with my hands. I stuffed the eyeball back in the top here. Hopefully that'll stay in there. Just held by the springs loosely. And yeah, hopefully it's gonna look okay. I think it is. I don't know. I'll find out. Stay. I might have to twist it around. I don't know if where the angle is, the shadow angle is, right? Because I haven't turned the thing on yet. Okay, so this is plugged in my isolation transformer and current limited variac supply, and I'm ready to go. So I just want to make sure that the volume is down. It is. As you can see here, the little volume moves up and down. I want to make sure everything is just down before anything happens. Okay, so here we go. It's on. That means that this switch is definitely on. Look at that. All right, so just wait till the tubes warm up. Aha! I see a green glow. That's a good sign. So it does have B+. The rectifier in the back here is working. That's washing out a bit because that's a very bright eye. So I'm just going to turn that around until it looks like it's somewhat supposed to be there, like that. So just loosely in place there. If I shine a light on the face here, it won't wash out so bad. You can see the eye a little bit better. But, okay, so I'll try and get that down here so it's not totally ruining the look of the face of the radio there. Okay. I can already hear radio stations happening here. So this is the volume, so I can turn this up.
Driver's seat for that top seat. So if they
wow. Not much eye action happening here. Wow. Lots of bass. So that's with the IF bandwidth down at the bottom here. Let's find something here. So what I'll do is I'll turn this up here. I should hear a lot of treble come in.
Winterizing. Yeah.
Leading up to Thanksgiving to keep gathering.
What's going to develop in the
If
to Peggy, because we try to come up with.
Wow.
Or not. Because in 30 states...
Craig, we should point out that it's some porn. That's all I want.
Wow. So it's really, really sensitive. Not bad, and it sounds so full. Amazing. The bass, this thing is rattling this speaker down here. So the 6L6s are driving that speaker very nice. So let's try another band. Let's see this one here. Looks like the switch or the bulb might be not all that great. Get that out of the way. This is a little bit brighter. So let's see if we have the WWV at 5 megs. Look at that. There's no RF alignment or oscillator or anything here. That's the time signal at 5. So this band goes down to 1.7, so I can get the 2.5 in here as well. Let's see how close it is to 2.5. You think you're so slick, radio? Let's see if you come in at 2.5. Okay, so here it is, 2.5. Okay, this is ridiculous. This thing hasn't even had an alignment. That's the 2.5 megahertz time signal. Okay, so this is 5.6 to 18, so let's see if we can hear anything at 10. No, this is 10 right here. So chances are I'm going to hear my own oscillator because I have a 10 megahertz standard in here. So I'll probably hear that. There it is. Wow. I think at 15. That portion of the band is out right now. Wow. Lots of bass in that. Okay, so let's go down to, I guess, the beacon band. Roll up here. That's a beacon right there. Wow. Wow. Well, the oscillator is pretty close. The oscillator itself on this thing is pretty close. So obviously the person in the past, this wouldn't be the original alignment, I'm sure, has done an okay job. Yeah, I would be very interested in the IF, knowing what's going on with it, because I noticed that when the IF bandwidth is narrow, it takes a lot to cause the eye to deflect in order to have a full deflection, so that the eye comes together, the two halves come together on a strong signal. It doesn't seem to do that with the bandwidth very, very tight like this. So I don't know if you can see that in there. I'll just get the light off. You can kind of see that. See how this moves up and down here. So with the IF bandwidth, they say low, fidelity low, so the bandwidth is very tight. The eye itself has a rough time deflecting. So I don't know if that's an IF issue or something like that. We'll find that out. So if I go to broadcast band here, so this is the bandwidth again. Let's see some volume. So you can see the eye doesn't really want to move all that much. Whereas if I like,
It's a funny hobby because
you can see if I widen it up, it's more sensitive when it's wide than it is narrow, which is kind of interesting. So that might indicate that the IF is definitely out of tune. And of course the RF section in here might not be as sensitive as it should be as well. So that would, cause this to be like this. Now this has, 2 IF amplifiers, right, and 3 IF transformers. And the reason that it has the extra IF transformer is because when you broaden the IF bandwidth, of course you lose sensitivity. Well, in this case, the sensitivity seems to be going up as we broaden the IF bandwidth. So the IF just might be really out of tune. So I'll get this thing attached to a spectrum analyzer, and we'll see exactly how things are. So I have to tune these little adjustments here. There's an adjustment here and an adjustment at the top, and then there's one at this one here and one down here, and then there's another IF transformer as well. So these little adjustments here are what I'm going to be twisting. Let's see, actually, just for curiosity's sake, if these are live. So let's see. I'll grab my voltmeter here, and let's see if these are live to the case. Sometimes they have B+ on them. So I'll turn this on to here. I'll put this up here for a moment. Very carefully. Let's see if I touch the chassis and this. No, they're not live on this. That one isn't anyways. So that's a good thing. I warn people about this a lot. Some radio receivers, the actual adjustments in the IF transformers are live. They have full B+ on them. So if you have a metal screwdriver, which you can turn these with just a standard metal screwdriver, if you turn these with a standard metal screwdriver, and if they were live and you slipped and touched the case, I don't know if you remember the game Operation, something like that. So, this thing will end up, shorting to the case, and you can damage the IF transformers. So you got to be careful around devices like that. These here aren't live, so that's kind of nice. So putting a screwdriver in is not going to be too big of a deal. Now, using a metal screwdriver in all cases is not possible, especially whenever you're dealing with powdered iron slugs. These are just capacitors, and this obviously are attached, to either the chassis or whatever. So the magnetism of the screwdriver, of a metal screwdriver in there, is not going to affect these. Now, a lot of the times, again, if you're going to be adjusting these things, and you can use a metal screwdriver in the capacitors, as long as it's insulated and it's not live, it's the better thing to do, because you'll break your tuning tools in these. These are, just big screws screwed into a capacitor here. If I had one of these caps out, I would show you. It's just a big threaded screw that tightens some plates together inside of a cap here. So normal tuning tools will get absolutely destroyed if you try to twist these, because normally these are very tight. So again, it's all about balance. Use a normal insulated screwdriver where possible, and then save your tuning tools for what they're actually needed for when you're dealing with powdered iron slugs and things like that. For those of you that are interested in knowing how I attach my spectrum analyzer to a radio receiver to do a sweep of the IF section, here it is. This is also valid if you want to attach just a standard sweep up to this, like using an oscilloscope and a sweep generator. This is the way that you do it. So first of all, you can see that we have the modulator tube here, which is just another name for mixer tube, and we have two input grids on this tube here. Now, normally, when a tube symbol like this is drawn, they have a little cap on the side indicating a cap, but they haven't done that on the schematic for all of these tubes that have caps. So what I've done is I've just drawn that in here. So the RF runs through the RF amplifier, through these coils here, and then up in this line into the cap, and that's the line that I'm going to be feeding the signal from my tracking generator of my spectrum analyzer. So there's a signal that comes out of my spectrum analyzer. All right, so the spectrum analyzer is running to the input line here. That's what SAN is. So the tracking generator puts a signal onto this line, and I want to put that signal into here. Now, I'm going to leave the oscillator running while I'm doing this alignment, and I'm also going to lightly couple my spectrum analyzer into this circuit. So when I'm attaching the signal into this grid line here, I'm not going to directly couple the output right to the cap. I'm going to clip the signal lead to the insulation of the wire running to the cap, and I'm going to very lightly capacitively couple into that grid. Now, the trick or the key to a successful alignment is to make sure that your test equipment remains invisible to the device under test. If, for any way, shape, or form, you heavily couple into a very sensitive tube like this or section like this, what you're going to do is you're going to drag your own alignment with the test equipment. And what you'll find yourself doing is you're going to align the IF section, and you're going to compensate for the mistake of heavy coupling. You definitely don't want to do that. That is the difference between a good and a bad IF alignment. Now, the trick to the whole thing is that when you're doing this, if you heavily couple in and you're, say, compensating for that by tuning these IF transformers, when you take your test equipment off, you don't know that you've heavily coupled, and the moment that you disconnect your test equipment from this, your IF alignment changes, because the capacitance and inductance added by your spectrum analyzer, the way you've coupled it in, is now removed, and that changes the way the IF looks. So very important to remember whenever you're dealing with an IF section and anything that's as sensitive as this, especially this line right here, you need to extremely lightly couple in. Now, what I've done is I've created some little boxes here. I've released this on YouTube. I believe it's under a spectrum analyzer protection device. You can look in my list of videos and you'll see how these are built. It's right here. It's released on YouTube. At any rate, my spectrum analyzer uses these boxes in line with the input and the output. So output of my spectrum analyzer being the tracking generator, and the input of my spectrum analyzer being the 1 megohm input of my 3585B. So what this does is this protects the input. This one here protects the input of my spectrum analyzer. So what happens is there's a limiting network in here with some diodes, and there's a whole bunch of capacitors in here that allow me to effectively keep everything flat during the IF frequencies. So the boxes are flat within the IF range, and it is a very tight range that these are flat in, but it allows me to protect the front end of my analyzer. So if I was to say, for example, accidentally touch this to some high voltage, I'm not going to take out the front end of my spectrum analyzer. If you burn out the front end of a spectrum analyzer, it's not like burning out the front end of an oscilloscope. If you burn out the front end of a spectrum analyzer, you're going to have a very bad day. So you don't want to do that. So I'm very, very cautious around the inputs and even the tracking generator output of my spectrum analyzer. There's another box like this that attaches to the spectrum analyzer output or the tracking generator, and it just says 50 ohms and high Z. It looks exactly the same as this. So it just protects the inputs and the outputs, and it's also an attenuation network in here so that I can properly tune these stages. Now, these boxes are purpose-driven or purpose-built, and again, you can check out how I've built these things right here on YouTube. Just look under my list of videos. Now, I haven't released the circuit boards or anything at this point yet, and I guess I should because I get asked for this all the time. I have another email today about, putting these things out. So I think I'm going to do that. So I'll probably add the files to Patreon as well. So if you want to build these things yourself, you can put some of these things together. So what I do, again, is I clip the signal lead just to the insulation of the wire that goes to the cap. And then, of course, the common just attaches to the chassis, and that'll feed signal into here. All right, and then what'll happen is by the time it gets through the IF amplifier into this stage right here, this is where I pick the signal back off, and this goes back into the input of my spectrum analyzer. Now this goes to the 1 megohm input of my 3585B, and I'm clipping it directly to the insulation again on the detector lead right here. This is a relatively high impedance point in this radio receiver, and that is very easy to drag. So again, with the isolation and attenuation of this box right here, this is the actual box that will be attached to that. I will just clip this right to the insulation of the lead, and this will clip right to the chassis, and that will pick up the signal and allow me to align this without dragging anything. That will give you the best alignment possible. So I'll get this all hooked up, and we'll take a look at the spectrum analyzer screen, and let's see how close or how far off the IF alignment actually is. All right, let's see where the IF is in this radio receiver. Let's see if it's close or if it's in outer space. So we know that the center frequency of the IF for this radio receiver is 465 kilohertz. Since this is a high fidelity radio receiver, I'm going to want a span of about 20 kilohertz. I'm going to want to see 20 kilohertz worth of width. So that means that if the center frequency is at 465 kilohertz, my start frequency is going to have to be 10 down from that, which just happens to be 455 kilohertz. My stop frequency is going to need to be 10 up from 465, so that'll be 475 kilohertz. So I'll set that up right now. So the start frequency will be 455 kilohertz. The stop frequency will be 475 kilohertz, and that puts the center right at 465. So I'll just leave everything the way it is right now, and I'll turn on the radio receiver, and let's see what happens. I'll have to make some other adjustments here. Let's just see where we're at. I also need to put this to the 1 megohm input, because that's what I'm on right now. There we go. Well, already I can see that I'm way off. So if I move the marker around, you can see a little marker right in the center here. If I move that around, you can see this is the peak right here, and that's where the center of the IF is right now. So we're right around 470 kilohertz. That's pretty far off. So what I'll do is I will adjust the dB per division here. 10 is a little bit, well, it's a little bit too much. So I'll bump it down to, say, 5 just to start off here. So the dB per division, 5 dB. That looks a little bit better. Now, in order to find out where this actually is, or to get as close as we can, what I'll do is I'll just press signal track here for a second. That'll bump everything to the center of the screen. And then, of course, it'll keep the span the same. So I'll just go signal track. And I'll shut that off. So there we go. The center frequency is right dead on 470 kilohertz. Look at that right there. So it's 5 kilohertz high perfectly. So that is way off. So what I'm going to do now is I'll adjust the fidelity control on the front of the radio receiver, and that should expand this. So we should see this widen up. This is on the narrowest setting right now. Whenever the IF adjustments are done, that needs to be done on the narrowest setting. And then once the IF is peaked up and everything's done, you can kind of critique it on the widest setting to make sure everything just looks good and everything flows properly. So what I'll do is I will widen this up. So I'm moving the fidelity control right now, and I can feel that little detent just starting to hit the cam right now. So I'll keep turning. And as you can see, I'm getting that gain. And I'll keep turning this, and I'll just stop this right about here. All right, so it stops hunting. What I'll do is I'll zoom on into the screen, and that'll give you a better idea of what's going on here. Right about there is nice and close. Pardon the shaky camera, I'll just adjust the focus here. And there we go. So that's at its widest setting. That's looking pretty messed up. So what I'll do here is I will narrow this up again, and as you can see, it's shifting. So you can see the peak is right in the center right there. Now you'll notice that as I showed you earlier, when I narrow the IF bandwidth up, the eye isn't working as well. Okay, so this is the narrowest. Now you can see as I'm widening things up, you see how that is rising on the screen? It's going up right now. As that's rising, what's happening is the IF section is becoming more sensitive. You can see that amplitude is coming up. Now as I get to the top, this is about the peak, and if I look at the front, it's about 3/4 of the fidelity control. So now if I keep going, you can see that it comes down again at its widest setting. That's at its widest setting right there, and as you can see, it's pretty wide. So again, I'll turn the fidelity control back down here so it narrows things up. You can actually see it, the peak is moving off center here as well. And then as I bring it back, you can see the peak, it kind of squeaks towards the center of the screen, and it gets to about the center right there. But you can really see the gain reduction. That's why the eye isn't working very well. So narrowest, and you can see, you know, keep in mind, this is 5 dB per division, right? So this is, if you want to see that, I can go here. You can look at this right now. It's 4.26, right? And I'll, like, look at how much that's coming up, right? So the peak would be about, what, 29 millivolts from, and that's from just coupling in right, you know, on the insulation of the lead. So we're down at 4, and we can get all the way up to 29 millivolts just by moving the fidelity control. Okay, so there's huge gain reduction there. So there's a lot of, you know, it's really out of alignment. So what I'll do now is this is the narrowest setting right here. So what I'm going to do is I'll just put one of my screwdrivers. You remember, if you recall earlier, I measured the capacitors on the front of those transformers to make sure that they're not live. What I'm going to do is the one that I measured, all right, I'll put a screwdriver in there and I'll just give it a bit of a twist, just that one, and let's see what happens. Okay, so it's in there. It's really hard to work around the tripod here. The radio itself has got adjustments on the front side, on the side, and on the back of the radio, which makes this extremely hard to do on camera. Not only that, to get the spectrum analyzer in the shot, it's sitting right in front of the radio receiver right now. So what I'm going to do is I'm going to make an entire, I think I should probably make an entire series on tuning radio receivers, doing the IF sections, and I'll have to create some, you know, other bracketry to hold cameras, and I'll go through that, the entire tuning procedure. Unfortunately, in order for me to completely tune this up, I'm going to need to do this off camera. The camera will have to be right out of the way, and I'll have to be moving the radio chassis around in circles in order to adjust this thing. It's just the way that they've set everything up. Some of them are on the rear, and the tubes are in the way. So I gotta move everything around. Okay, so here we go. I'm gonna move that bottom capacitor. So you can see I'm moving the gain around, and now you can see I'm actually shifting the center. So what I want to do first of all is tune for the maximum at 465, so I can move this here. It actually shifted it in the right direction. So right about there. So if I move the marker over, see I'm about 468 now. You can see how much that shifted it. So I'll move the capacitor in the top side of that, and let's see what happens when I do that. All right, if I can get my screwdriver in there. This one's almost behind the dial glass. This is a okay. So give this a bit of a twist. Wow, look at the amplitude coming up. So right now, by doing this, as you can see it rising on the screen, look at that. That's sensitivity. That's receiver sensitivity that you see happening right there. Lots of sensitivity added just by moving this around. So right about there is its maximum sensitivity at about 468. So you can see, just by tuning those two capacitors, how much this is already improved. I've actually shifted this closer to where it's supposed to be at 465, and the sensitivity has come right up just by tuning two of those capacitors, just two of them. And there's another two transformers, so that's four more of these that I get to tune in order to bring this up. So it's way out. You can see that it's absolutely way out. So when this is done, the eye should work very good, and I should get a very nice even spread on the IF when I'm done. So chances are it'll probably have a stage curtain effect. So you get the double hump kind of happening on here. And once I've got this all perfected, I will come back and I'll show you what I've done, and I'll explain it. To give you an idea of usually how long it takes to do an alignment like this, you're looking at, in order to perfect everything, to make it look as even and to get the best results possible, it usually takes me about an hour or an hour and a half to do this. And that's just moving back and forth between capacitors and just making sure that everything is right where it should be. And of course, you want it to look just as good when you're widening things up like this. You can see it doesn't look too bad there. You can see the double hump right here, right? But that's just, that's nowhere near the end of the fidelity control. Like, that's the end of the fidelity control, okay? So you can see that it's starting to look a little bit more like it should, and that's just by tuning those two capacitors. So you get the stage curtain effect, the double hump happening here. So again, I'll get all of this done, and I'll show you exactly how this should look, and then we'll be on to the RF and oscillator and antenna section tuning as well. Tuning the IF section in the Stromberg Carlson took about an hour and a half, and that is an hour and a half of me moving around those 6 variable capacitors in those 3 IF transformers. Now, I have to tell you that getting the IF to work the way that you're going to see it here on the screen without using a visual means would be absolutely impossible with this receiver. I'm telling you, if I look at one of those variable capacitors out of the corner of my eye, this pattern that you see on the screen will change dramatically. That's really how sensitive it is. It's so sensitive, in fact, these radio receivers sounded fantastic when they rolled off the factory floor, I'm absolutely sure. But the moment that somebody changed one of those IF tubes or even the detector tube, this pattern would just change. You wouldn't have that same quality of sound that you would have had when this thing came from the factory. I'll give you an example of that here in just a moment. So you'll see that the center of the screen is exactly at 465 kilohertz. Now what I'm going to do is I'm going to widen up the IF bandwidth, and you're going to start to see that stage curtain effect. Now, the whole trick of making these IF alignments work the way they should is to keep that double hump falling and rising evenly. So the stage curtain effect, those 2 bumps you're going to see on each side, they need to fall and rise evenly as you're moving around the variable IF bandwidth. So as those 2 slugs are moving up and down inside those 2 IF transformers, they need to basically work with each other correctly in order to get the sound. All right, so I'll give you an example here. All right, so I'm coming right to where this little detent is now touching the cam to where it's going to start moving those slugs. So here we go. Now keep in mind that this is now at 2 dB per division. I had it at 5 dB before, but at 2 dB you can see much more detail here, okay? So now you can see how it's widening up. Okay. Now you can see how I'm getting the stage curtain effect. You see how we have those two bumps on each side? You see how they're forming evenly? That is a very difficult task to achieve, because you'll get a bump on one side and it'll maintain, you know, a flat mark on the other side here. So what I'll do is I'll move this down to its widest IF bandwidth, and as you can see, they fall evenly, and as I raise this, they rise evenly, and then they form the perfect bell curve in the center. And then as we come to our narrowest bandwidth, you can see the amplitude dropping just a little bit. Now that's absolutely normal, right? And keep in mind, we're also dealing with only 2 dB per division here. So what you're seeing is very, very minuscule. So making this happen, just like you see right here, and then falling evenly, like this, is the result of about an hour and a half of tuning. That's going back and forth between all of those capacitors and making sure that I maintain the 465 center, and then I have those two bumps forming on either side. Now this is the best it's going to get. You'll see right at the center, right at the very center of the dip here, I'll just move the marker around. You'll see right at the very center here, you can see the little marker moving around there. So you can see that the center is off really just into the hertz, right at the bottom, right? So absolutely fantastic for an IF section that was designed in the 30s. In fact, this is really quite amazing how well Stromberg Carlson put this together. So what I'll do is I'll give you an example. If I just I'm telling you, touch, I'll just move this back to the center here again, so it's right at the center. If I just push on one of those capacitors with a screwdriver, watch what happens to the pattern here, okay? So I'll just get over here, and I'll put a capacitor, or a screwdriver in the capacitor, and I'll just press on it. See that? Now, if I was to give this a twist of a hair's width, we'll say maybe a millimeter. Look at that pattern. The pattern is immediately destroyed. We're talking moving that hair's width. All right, so I'll adjust the IF here so you can see what's happening. So you can see it forms somewhat even at the center there and comes back down. But then once we start to widen it up, we get one bump that's way off to one side. So our peak sensitivity will be off to one side of the IF. And as you can see, that's just really in outer space right now. That's by moving just one of those 6 capacitors a hair's width. So you can get an idea of how long it took to actually figure out how to make everything track and, just have a good pattern here. So I'll put this back in here and I'll try and get this adjusted perfectly again. Probably have to spend some time with this to get that right where it needs to be again. We'll just leave it there for now. And I will move this around. So we'll see this rise. That's very close. And it forms right at the center. And that's the narrowest bandwidth right there. So as I say, doing this by just a peaking method or using a VTVM or something like that would be impossible. It would be absolutely impossible to get what this is doing right here. So this radio receiver with that IF that you see there will sound fantastic. It will sound like an FM radio when it's wide. So what I'll do here is, since we're at our narrowest position here, what I'll do is let's calculate to see how wide the IF actually is. So I'll just make sure that that's at its narrowest point. It is. So I'll adjust the reference volts here and just bring this up to the top line. So we'll go here. That's pretty close. So if we go 24.5, and that's 21. So let's say, we'll say 23.5. Let's try that. 23.5 millivolts. That's a little bit too high. Let's go 24. Go reference volts 24 millivolts. That's very close to the top line there. Okay, so what I'll do is I'll turn on the display line, and I'll move the display line right up to the top. So if you look here, you'll see that this comes to 0 dB right at the top line there. Okay, so since this is 2 dB per box down, I need to go down 3 boxes. All right, so I'll move this down 3 boxes, and as you can see, right at, you know, minus 6 dB right there, and this is where they normally measure the IF width. Okay, so I'll go back to the marker, and I'll move the marker off to one side, and I'll put it right at that line. Okay, now we're at 467.08. All right, so I'll get my calculator here. So 467.08, and then we go take away. So I'll go to the other side now. 462.92. 462.92 equals. So we're dealing with 4.16 kilohertz of bandwidth. Not bad. That's pretty narrow, so it's very decent for communications quality stuff. So that's going to allow us to really narrow in on frequencies that have, you know, other frequencies very close to them. So we can, you know, really just get rid of all of the adjacent frequency noise. So it's pretty decent, not too bad. And that's at 6 down. Usually I measure them at 3 down, right? Because 6 is actually being kind of generous. They were always kind of generous doing that. But we'll just stick with the 6 because that's usually where these companies measured them. Okay, so 4.16 kilohertz wide in the narrowest position. So now let's go to the widest position and see what happens here. So I'll have to probably bring this down to center screen here. So reference volts, bring that down to about here, and I'll bring this back up so we can adjust this here in a moment. Okay, so oops, bump that controller. Let's go here. So we're at 15.1 and 17, so let's try 16. 16. That's pretty close. Close enough. All right. All right, so we're still at the 6 dB down point. You see the display line here is still at the 6 dB down. So if I go to display line, you'll see minus 6 dB right here. That's this line, again, 3 boxes down, right? 2 dB per box. All right, so what I'll do is I will roll the marker back over here. All right. I bumped the display line. It doesn't matter. I'm using the Graticule anyways. So I'll go back to the marker. So right there, we're at 475.6. Okay, so we'll go 475.6, take away, over to the other side now. 454.560. In fact, I might be able to move that down just a touch right there. So 454. Let's see. Get this as accurate as possible. Right about there. 454.560. All right, take away 454.56 equals 21.04 kilohertz wide. Pretty fantastic for an IF section. So we'll go divided by 2 equals 10.52. Okay, so this is 520 cycles above their audio cutoff filter that they've designed on the underside of the chassis. Can you say Stromberg Carlson did their homework? What a fantastic job. We're only 520 cycles above. Right, so it's 10.52 each side of the center. This radio receiver will sound absolutely fantastic. So there you have it. That's how the IF should look in one of these radio receivers. Keep in mind, if you're ever going to align something like this, you need to make sure that these things fall and rise at the same time. You want to maintain symmetry as close as you can to their design. And again, you can see that the center is out just a touch, but it's in the hertz here. If we move this right here, see the little marker here? Technically, that would probably be the dip right about there. You know, so not a big deal. Not a big deal at all. It's so close. For IF transformers designed in the 30s, this is ridiculously fantastic. So anyways, let's get on to the other portions of the alignment. I'm going to perform the antenna and RF alignment in this radio receiver. I'm not even going to bother with the oscillator adjustment because the frequencies, as displayed earlier, are spot on. And it's, yeah, this thing is so incredibly close. I've actually never come across a receiver that is this close without me doing an alignment on the oscillator section. So these are the oscillator adjustments here that don't need to be touched. This is the RF adjustment here. You can see RF written there. This is the RF adjustment. So in that box there is the RF coil, and these are the tuning capacitors. And this is the antenna adjustment right here. So I will adjust this one here and this one right here for the broadcast band. So I have my signal generator set to 1500 AM or 1.5 megahertz. And I'm at 100 microvolts. So I'll just move the dial to 1.5 megahertz here. 1700. That's so ridiculously close. Listen to that. It's spot on 1500. And that's with the IF width narrow. It's right on the line. Again, I've never come across a receiver that's ever hit the bench that's been so in tune that way. It's actually kind of surprising. So now that the IF section is done, we can use the I itself as a tuning aid. So I'll just tune this off frequency here again, and I'll show you that the I is functioning correctly. And I shield some of the light from it there. Maybe a little bit. Okay. There it is. So I can use this as a tuning aid. I don't even need to hook up a VTVM or anything like that. Now the capacitor that's in this circuit here, the time constant for this is a little bit slower than I would like it to be. I'm almost tempted to modify that in the design. I'd like this to respond a little quicker, but that's okay. Okay, so what I'm going to do is adjust the antenna section here and just tune for a peak. So I want this to come as close together as possible. And I have a feeling this is probably spot on as well. Okay, so let's see where we are. Oh, no, I can use a bit of a peak. Right there. And then I go over to the RF, which is right here. I don't think I can aim for this without tipping the chassis here because it's right underneath the camera. So I'll just move this like so. And put this in there. It's a really big chassis, really awkward to work with here on camera. Okay, and I'll tune the RF section. So again, we're tuning for a maximum closure. Right there. The thing is really spot on. Now, if I was to touch the oscillator adjustment right here, it would just tune this thing off frequency. That adjusts the dial tracking. So I definitely want to be touching that because when I say this thing is spot on, it is spot on. So this eye tube here is looking okay, but it might be a little bit tired. I think I might just grab another eye tube here. It's nice and bright, but doesn't seem as sensitive as it should be. So give me a second here. I'll just unplug the eye tube. And I have another one here across the lab. Okay, so here's a brand new one. This is a JAN type 1, Joint Army and Navy 6E5. So this is going to be a really nice tube here. Plug that in. Let's see if that's any better. This is brand new, so it might take a few moments to come to life, so to say. Some of the light off of that there. Yeah, it's definitely closer together. I'll just move this off frequency here. That's definitely more sensitive, and it's quite a bit brighter as well. So I think I'll leave this one in there. That's very, very bright. Very nice eye tube there. So now what I'll do is I just have to go to the other bands, do the exact same thing, just basically rotate the band switch here, like that, and then go to the next band and tune it. So I'll start at the bottom, I'll start with band X, and that's these adjustments here in these cans. Here, I'll see if I can show this to you. Well, this thing falling off the bench. This ridiculously awkward thing to work with. That's tuning these right here. And then I just have the rest of them to tune, which are here. So, very simple alignment. Everything, as I say, the whole oscillator section here seems to be right on frequency. So the person that was in here last really did a good job in aligning the RF and the antenna in the oscillator section, but wow, that IF was in outer space. So everything good except the IF really was aligned okay by the previous technician. Another portion of this radio receiver that has been most likely detuned over time and never retuned properly again is this 10 kilohertz audio cutoff. So there's a little filter network down here, there's a little inductor and a capacitor across it that's designed to cut off the audio after 10 kilohertz. So this is between the last audio amplifier and the grids of the 6L6s. Now, there are no instructions on how to adjust this in the alignment procedure, so that's something that was done at the factory, and I guess they just expected you to leave it alone. I would imagine way back when, Stromberg Carlson had a sweep setup for the audio section in this as well. So I'm going to use my Stanford Research SR780 to sweep the audio section, and I will make that adjustment so that we can cut that audio off after 10 kilohertz. I'll get that set up, and I'll be right back. The Stanford Research SR780 is attached to the radio receiver, so the source output, or the signal coming out of the Stanford Research SR780, is fed to the wiper of the volume control. And the input of the SR780, so the signal going back into the analyzer, is just picked right off the voice coil of the speaker. So I have the sweep set from 8 kilohertz to 12 kilohertz, and that should get us within the range of this adjustment here. And we should be looking for a dip or a null around 10 kilohertz. So I've got the marker set to 10.02 kilohertz. The reason it's sitting at 0.02 is just because of the number of points I have here. If I up the number of points, it'll sweep slower. And the slower sweep is painful to work with, so we'll just leave it here. 10.02 is close enough. So I'll turn on the radio receiver and wait for the tubes to warm up. And the analyzer is set to auto range, so it should pick up where we need to be here. Let's see where this thing is sitting. Oh, I see something on the screen here. So we can see the dip or the null is actually quite early. So let's see where it's sitting here. It's sitting around 8.5 kilohertz. That's no good. It's supposed to be at 10. So I need to move that dip over to this line over here. So what I'm going to do is insert my screwdriver into that adjustment that I just showed you. And I'll give it a bit of a twist. Okay, see which way are we going? Oh, that's the other way. We don't want to go that way. So let's try the other direction. Now I have to wait for the analyzer to catch up because it's a slow sweep. So we're going in the right direction. That is a good sign, and there is quite a bit of adjustment room here, so that's good. Well, I'm just about there. One more little tweak. Oh, I passed it. See if I can see how far I can actually go here. Whoa. So you can see I've completely passed it, so I'll back the control up until that dip is right in the middle of that line. So every time the sweep goes past, I give it just a bit of a turn. So let's see how close we are here. A little bit more. A little bit more. I'm just moving this control a hair. And I think that's it right there. That's looking pretty close. So let's up the number of points here. So let's go let's try 500. Enter. And I can probably move the marker. I think that's as close as I can get right there. 10.003. It looks like it's spot on. That is a slow sweep. Yep, it's right in the dip. The radio is all put back together. Let's cruise around the broadcast band and see how this thing sounds. So hopefully the mic will pick this up. I have it pointed towards me, so it'll hear me, but it is a really full sounding radio, so let's get some volume here. You can see as I'm turning the volume up, it moves that little scale up over there. It has this little red dot on one side, which seems to be almost a perfect volume all the time. So that's kind of interesting. Okay, here we go.
Research Institute's life-changing outreaches.
Government officials on the program again. You'll have the guests you need. Sports news note and long-term care workers in every area of the province.
Incredibly full sounding radio, and that's not even at the most fidelity.
People, countries banning travel. Thank you.
Very full, like stations absolutely everywhere. The radio itself turned out very nice. I'll give you a view of the front of the radio here. You can see the nice gold leaf in the grill there. It turned out really, really nice. I cleaned up the wood just a little bit. Basically really didn't need too much, right? So that worked out well. So let's try another band here. Let's see. We can go to the beacon band. This is aircraft beacons down here. So what I can do is zoom in just a little bit more. Actually, no, this lens is going to allow me not to zoom. So let's just give this a shot. Let's take a look. Give us some volume here. Another one here. And that's right down at the bottom. Not a whole lot down, around 145 kilocycles. That's way down at the bottom. That's way below the IF frequency of this receiver here. So it stops at about 360. It says 370 right here. I think 360 was the last. That's far enough away from the IF so that, 360. So it's 360 there, and the last would be 370 right about there. So, yeah, it's way, way, way down there. Now, they have police written here, but I think that's for the next band up way, way, way back when. So let's up the fidelity just a bit, and let's see here. Maybe I can find something to give you a better example of how the high fidelity really sounds on this. Problem is that you need music to do that, and we know how that works on YouTube. So let's see here. If I can find just a station that has pretty clear talking.
Biblical language and go to great lengths to concoct commonalities. However, the alleged similarities as well as the terminology used to communicate them are clearly exaggerated.
Isn't that fantastic? That's full fidelity. It sounds like the person is sitting right in front of me. It's just incredible. So I'll just go to the next range up here. And let's see. These ranges, the higher you get in frequency at this time of the evening, it gets really quiet. We'll see if I can find, let's see if we can find the WWVB, or WWV, I should say. The VB is down at 60 kilocycles. This to WWV should be at 2.5 at this time. There it is. I don't know if you can see the action of the eye. It's kind of blown out here. Let's see if I do this. All right. And I'll just now, if you remember the IF curve way back when we were doing the alignment, you get a certain way through the fidelity, it comes to a peak and then it comes back down again, and you can really see that with the fidelity control, even with just the noise. So what I'll do is I'll bring this to the start. Okay, so this is the start of where the cam is just touching the slugs. Now, as I increase the fidelity control, you'll see just from noise, the actual eye will close. So that's its peak right about there, and then as I go to full fidelity, it opens back up again, just a little bit. Right about there is full. Right there. I don't know if you can see that. Very little change, right? But at any rate, that shows you that, this is following what we've done in the IF. So very interesting. This sounds the best right about there, about 3/4 the way up. So anyways, let's let's go to the other one. That's 5 megahertz is the other time signal. That's very strong. So I don't know if you can see that. That's going to defocus there. It's pretty much closed. So I'll go off frequency. Lots of noise. I have this hooked up to a really large antenna. So this wants to receive lots of stuff at this time of the evening here, and this is this band is pretty active. There is shortwave broadcast in here. This is pretty much between the 80 meter ham band and above. And this is all quiet down in here. Oh, there's some sideband in the 80 meter band. Well, somebody was there a moment ago. And the upper band will be just pretty much quiet at this time. See if we can see my oscillator at 10 megahertz here again. There it is. So that's my own standard here. So there's a little bit of shortwave broadcast there, as you can see at the lower end of the dial at the top here. This comes to life during the day, and this is this here will actually I'll just bring you back to full brightness here. So this comes to life during the day at the top band here. This is kind of middle to end of the day and in the morning. And then, of course, this is the beacon band here, which is, going to be active most of the time, at least with local beacons. So all in all, let's leave that here. Let's go back down to here and move this up to here. So all in all, like the radio itself is, it's working just absolutely fantastic. Out of most of the radio receivers that I have restored, I honestly have to say the Stromberg Carlson is probably the most enjoyable to use, really. The fidelity control, as you heard, is just makes AM listening fantastic. Now, you can't really use the fidelity control if they're station on station, if they're very close together, because the IF just goes so wide that you're kind of into the next frequency already. So when stations are piling up, you have to have this narrow, and it really does narrow into the frequencies quite well when they're very close together. So that variable IF width really does help. Tons of audio driving power. It gets quite uncomfortable after that dot. This is the dot right here, and as you can see, I'm kind of raising my voice. After that, it gets absolutely crazy. So those 6L6s are driving the speaker. The difference of having that speaker sitting in this cabinet with the acoustic labyrinth behind it is somewhat amazing. The bass frequencies, the lows that come out of this radio receiver are absolutely astounding. The lows are just, I don't know how to even describe it. I was listening to some country music and just all sorts of different things on the AM band here earlier, just trying to find as much different music programming as I could. And it sounds like FM, really, it does. The bass is just rumbles the place. If you have a chance to get one of these radio receivers, if you find one of these Stromberg Carlson 145s, I strongly suggest, if the pricing is right, pick it up and put the time into it to restore it. If you like listening to AM and you like these old radio receivers, this radio is nothing short of fantastic. It really is.
Basic courtesy in marriage.
Yeah. I'm thinking of that either husband or wife, and I'll use the wife because I think it leans that direction most often, where she doesn't feel connected any longer, emotionally, spiritually, maybe even physically. She's drawn into this conversation. Okay, there's some things I need to do. Maybe it's the husband.
There's a better example of how this sounds with the microphone more optimally placed, let's put it that way. The only way to really appreciate the fidelity of this radio receiver is to just sit in front of it. I realize in the last shot the audio is a little bit boomy, but I was trying to get myself and the radio at the same time, but unfortunately there's a lot of room echo in here and everything like that. I just about left out the capacitor of doom. Here it is. This is the capacitor of doom that came out of this radio. So this is the factory device. It is actually shown in their parts list as a little half circle on the side of the chassis, and this is the thing. It's clipped in a little hole here on the bottom of the chassis, so it kind of runs through the side of the chassis, and then they bent this tab up. Original device. So let's see how bad the capacitor of death actually is. So there's a lot of misunderstanding around the function and about the function of this particular device here. So AC line cord decoupling and all sorts of things to do with RF and EMI and all sorts of things. I'll get into the exact description of what these capacitors do. Their functions vary within different devices actually, but you'll see the same kind of setup. Sometimes you'll only see one, sometimes you'll see two, sometimes you won't see any at all. It just depends on the actual device itself that the death capacitor is in. In this case, it's an actual radio receiver, so it's doing multiple things. At any rate, so what happens is this thing ends up failing. So they short, and what they do, one side will short, and if both sides short, it'll take the fuse out. But if one side shorts, what it does is it'll take one side of the line cord and put it directly on the chassis. So that's not a very safe situation, is it? So that'll cause some issues. The new replacements to these capacitors are these ones right here. So this is known as an X1Y2 rated capacitor, and they have all sorts of safety ratings on them. And these are designed to fail in a safe manner. I won't get into the failure points of these capacitors and get too deep into the caps here. But at any rate, this should be replaced with a very safe device. If you're restoring radio receivers that have these caps, it's an absolute must to get rid of these things. You don't leave these behind like the previous people that have gone through this radio receiver. So you definitely don't want anything like this to go bad. So let's take a look at what's actually going on with this thing here. So this can be directly, the scale on this device can be directly converted into ohms. So basically what this is going to do is it's going to look for the resistor that this thing is trying to turn into, okay? So this is a very sensitive device. This thing will go up to 40 billion ohms in the forecast position to really look for any type of leakage, any type of resistance that may be hiding in these capacitors due to just it degrading, moisture ingression, all sorts of different things. Again, a very purpose-driven device. So the first scale is red. That's a really bad scale. And then it starts off at the yellow scale on the second scale, and it works down and it becomes green at about 40 billion ohms. All right, 40 gig ohms if you prefer. So let's see how actual bad this thing is. First of all, you know what? Let's test a new one. Okay, so this is a brand new capacitor here. Okay, so what I'll do is I'll just I can turn this on. It'll read the resistance of my hands as I'm holding these things. So I'll just have it in the test position to begin with. It doesn't really matter. So again, it's a low voltage tester. So, you know, there's no issues here whatsoever, right? So the first scale is red, as you can see. When I'm holding these here, I'll bring it up to the yellow scale. To the top of the yellow scale is about 1 billion ohms. Okay. And then if I short them together, you'll see that that's a dead short. So that's the start of the scale right there. And then anything beyond this is about 1 meg ohm, and it works its way up to 1 gig ohm. The scale flips and it goes from 1 gig to 40 gig ohms. All right. So I'll put this on here. So there it is. Okay. It's on the test. And as you can see, it's comfortably going up to 40 billion ohms and beyond in the forecast position. The forecast position on this thing is the most sensitive position there is. And again, if I just touch the boots of this very, very lightly, you can see that I'm discharging that cap at 40 billion ohms. So it's reading my body resistance through a vinyl boot. So it's reading the resistance of this boot, of my entire body, and then back to this boot here and the resistance again. Okay, so you can see that just by lightly holding that. So a very sensitive device. Again, it was designed to look for obscure issues. So here is the death cap. Okay, so I'll put the positive lead there. Now don't be confused. You can see a chassis ground symbol. Don't be confused by that. This is an alternating current capacitor, and it really doesn't matter. These capacitors are not electrically polarized. So it's in a shell, and of course it's designed to be across an AC line. So the polarity is flipping around all the time. So let's test these out and see what we get. All right, this should be interesting. That here. I want to make sure the boots don't touch anything. So as you can see, that's pretty bad. So that's going to be just below 20 meg ohms. So this next light up will be 20 meg ohms. All right, I'll grab this resistor here just to give you an example. I got a bunch of them put together. These are 20 meg ohms each. All right, so the 20 meg ohms should be the next light up here. So very, very bad. So you can read, you would actually be able to read this. It's so bad you could read that on a standard DMM. Okay. This here goes way beyond a standard DMM. So there you go. So that's 20 meg ohms right there, right across that one resistor. And we're below 20 meg ohms with this. So if I was to put this across a DMM, it's going to read very close to, you know, I'd say between 10 and 15 meg ohms. Okay. So you can see that, you know, this capacitor is really bad. Let's test the other one. So we tested one here. I think it might have been that one. This is the one that we've tested here. So it'll creep up to just below 20 meg ohms. Okay. And let's test this one here. And this one here is open. Oh, no, it isn't. So this one's on the verge of shorting out. This would have been the side that would have most likely caused very bad issues. You can see this thing? It's in the red scale, and it doesn't know what it's doing. Look at that. So right now, if this was attached to a line cord, it would be inside, it would be shorting out. It's sparking, it would be sparking and doing all sorts of things inside there because it's intermittent. And as you can see, it's intermittent in the red scale. So it's really, really bad. So this would have been the side that caused the issues. So now, depending on what side you plug this into the wall, okay, because remember, this is putting low voltage across this, and this is seeing this issue right now. So the line cord that's on this thing isn't polarized, so you can plug it in this way or plug it in this way. So there's a really good chance that you would have put the hot side on this, and that would have been connected to the chassis. And as you can see inside, it's intermittent. It's basically, this would be, you could say, sparking inside right now, or sizzling inside there right now. And I can almost guarantee if this was plugged in, the next time this was plugged in, that would become a dead short. So it would have attached the line cord to the chassis. So how do you like that? That was caught just in time. This other side here seems to be pretty constant. So this one here wasn't doing the same thing. This one here is just showing a fixed resistance. So that other side would have been the extremely dangerous side. So crisis averted there. So just think, somebody had worked on this thing and left this thing in there. And that was on the verge of happening. The chassis of this radio receiver was on the verge of becoming live. And who knows if these would have actually shorted, it would have taken that fuse out, right? That little fuse would have gone away. And that's hard on things. You know, it's hard on the power switch, and it's hard on all sorts of things. So definite crisis averted right there. Big time. At any rate, if you're interested in building one of these things, again, this is on Patreon with all the plans, along with many other of my creations up there. Definitely check it out. If you're enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid state electronic devices alike. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, and gaining access to many of my personal electronic inventions and designs, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description under the Show More tab, and I'll also pin the link at the top of the comment section. So if you click on the link, it'll take you right there. All right, until next time, take care. Bye for now.